And the next speaker is also the main coordinator of this today of the workshop. So Virginie Rondeau from ISPED.
So good afternoon, everyone, and thank you all for this introduction. So I'm going to talk about prediction also, and we have worked on a dynamic prognostic tool using joint modeling in order to take into account the evolution towards recurrent event until death. So I'm going to illustrate this kind of development using a breast cancer cohort. So this is a collaborative work which has been done with my PhD student Audrey Maugret, also with Bernard Rachet from the London School. We have collaborated also with Simone Latour-Bellissier and Gaëtan Labrogan for the dataset. I have worked also with Alexandre Laurent in order to develop the software and myself. So after a first diagnosis of cancer and of breast cancer specifically, we can see and we can measure some, or we can evaluate different events after the first diagnosis. So for instance, after a first breast cancer, the patient can develop local regional recurrences of his first cancer, or he can also develop distant metastases and then death. So we wanted to take into account the different events, which are recurrent events, which can influence the prognostic of the patient. So the interest of the prediction is prediction of death are several interests. First, it can be a clinical interest, simply because it can help the clinician to choose between different treatments. And of course, when the prognosis of the patient is bad, we can add new treatment, but when the prognosis of the patient is good, we can sometimes remove some cytotoxic treatments. The prediction can also help the clinician in order to monitor the patient. So sometimes when the prognosis is bad, we can imagine to follow more frequently the patient. The prediction also can help the patient in order to inform the patient for his future prognosis. And sometimes prediction can be used also in the trials, in the definition of subpopulation, in clinical trials. So usually, as it has been shown this morning, usually when we use a dynamic prognostic tool, it takes into account individual characteristics of the patient, but also the tumor characteristics. And sometimes when we have the information, we can also adjust in this prediction tool, we can adjust for the previous treatments. And in recent articles by Cécile Pousse-Limin and Dimitri Rixopoulos, it has been shown also that it was nice to take into account the evolution toward longitudinal markers when we want to make prediction of death, but also prediction of the progression of the cancer itself. So the motivation of this work was to analyze a large cohort of patients with an initial breast cancer, and these patients were treated in Bordeaux in the Comprehensive Cancer Center. They have been followed until 20 years, and during this follow-up, after the diagnosis of the first cancer, we were able to observe recurrent events. So in this case, we are going to define recurrent events like successive events that can occur during the follow-up as local regional relapses or metastases. So we are not going to distinguish between these two types of recurrent events in in this work. So in this example, in this plot, we could observe until 3 recurrent events per patient. So in this work, we assume that the evolution towards different recurrent events can have a major influence on the prediction of death. So we wanted to predict, using a dynamic aspect, we wanted to predict death in a time-varying window using a prediction time t and the horizon time t plus h. We wanted to predict death using different information. The individual characteristic of the patients, but also the occurrence of the different recurrent events. So we were interested in the number of recurrences here before the event of interest, but also the time of occurrence of these different recurrent events. So in order to propose a dynamic tool using these two aspects, these two processes, the recurrent event processes but also the death processes, we are proposed to use a joint modeling approach. So in this joint modeling approach, we are going to joint model the recurrent events and the death process using a joint modeling approach, and we assume that these two processes are highly correlated. So previously, when people wanted to predict death and when they wanted to take into account the evolution toward a recurrent event, they use a Cox model and they use an adjustment for using time-dependent covariates for the occurrence of recurrences. However, we have to keep in mind that when we use a Cox model with time-dependent covariates, the time-dependent covariates should be external covariates, which is not the case when we adjust for the occurrence of recurrences. So this is why the Cox proportional hazard model adjusted with time-dependent covariates is not the most appropriate method in order to analyze this kind of data. So this joint modeling has several entries. First, it enables us to investigate and to quantify the association between the risk of recurrences and also the risk of deaths. And in this kind of joint modeling, we can evaluate prognostic factors associated to recurrences but also to death. And we can treat the informative censoring by death in this kind of model simply because death and recurrent events are associated events. So I'm going to introduce some notation. So T is going to be the time of prediction and H the window of prediction. We define D of I is the time of death for the subject I. And for each subject, we are going to observe different recurrent events. So we define Xij, the time of recurrent event for this, the different time of recurrent event for this subject. We can distinguish two kinds of prognostic factors. Prognostic factors associated to the recurrent events, but also the prognostic factors associated to death. And in this case, we were interested also in the estimation of the baseline alpha function for the risk of recurrence, but also for the risk of death. So this is the expression of the joint modeling. So this is a joint modeling between the recurrent event process first and the terminal event process. These two functions are linked using a random effect, which is shared by each subject. So in this case, we are not going to estimate directly the value of the random effect, but we are interested in the variance of the random effects. So these random effects are going to correspond to different unobserved covariates, which are linked both to the recurrent event process but also to the death process. So we have to choose also in this kind of model between two time scales, a gap time scales, it corresponds to the time between two recurrent events for the first part of the model, or a calendar time scales, which corresponds to the time since the entrance into the study. So the theta is going to correspond to the correlation or the association between recurrent event and death, and alpha adds more flexibility into the model and is going to say if unobserved frailty is going to have a more important effect or lower important effect on death than on recurrent event. So in order to estimate the parameters in this kind of joint modeling, we use a penalized log likelihood simply because we wanted to have smooth hazard function, and we made an approximation using cubic spline in this expression. And of course, because we had random effects, we had to solve the integration using like Gaussian Hermite quadrature in order to solve the integration. So in this case, we have different parameters to estimate. The baseline, the parameters associated to the baseline function, the parameters associated to the prognostic factors, but also the parameters for the heterogeneity associated to the correlation between the different recurrent events. So when we wanted to propose the dynamic prediction probabilities, we consider a patient which was free of death at time t, and for whom we observe J recurrences before this time. And we observe also for this patient a vector of covariates, and this vector of covariates was known at the time of prediction. So when we have this kind of recurrent events, it is important to define the history of the patient. So in this case, we define the history of the patient as the number of recurrences occurred before time t, but also the times of the different recurrences before time t. So we are going to see then after that we can choose different settings when we define the history of recurrences for each patient. So we have distinguished the three settings for the probability of death between t and t plus h. In the first setting, we wanted to say that we are going to predict death between t and t plus h, given that the patient has developed exactly n recurrences before time t. In the second setting, which were more flexible, we wanted to say that we are going to estimate the probability to develop death during t and t plus h, given that the patient has developed at least 3 recurrent events or n recurrent events. And in the last setting, we didn't take into account the history of recurrent events before time t. So it's close to a naive approach, which doesn't take into account the evolution of the patient toward recurrent events. So in more detail, in the first setting, so as I said, we wanted to adjust on the number of recurrent events before time t. So in this case, when the patient arrives to the clinician, we say that he has exactly n or j recurrent events. So when we write the expression of the prediction, we obtain that this prediction depends on the random effect with the power of using the number of recurrent events and the survival function for the J+1 recurrent event. So as an example, we can say that up to now, Mr. Martin has developed 3 recurrences of his initial cancer. So we are here and we want to make the prediction in the next 5 years. So we can say that in the next 5 years, given his history, is going to have X% of deaths. In the second setting, we said that the patient has developed at least J recurrences before time t. So when we write the expression of the probability to make the event between t and t plus h, given that he was still alive on time t, we obtain this expression, and in this expression we can see that it mainly depends on the time of the last event. So as an example, still Mr. Martin has already developed 3 recurrences. So if he's still alive in 2 years, his probability to die in the next 5 years will be of X%. So it's a little bit different than what we have seen previously. And in the last setting, so as I said, we do not consider in the prediction probability, we do not consider the history of the patient, but we consider the history of the patient in the estimation of the parameters. So at the end, in this expression, we do not have anymore the number of recurrences which are involved in this calculation. So we can have several interpretations of this probability. First, we can say that this probability of dying in the next 5 years is X%. Or we can say that if Mr. Martin is still alive in 5 years, this probability of dying over the next 5 years will be of X%. So, as it is usual, we have used, in order to evaluate the variability of the probability estimators, we have used a Monte Carlo approach. So we have generated the parameters using the multivariate Gaussian distribution, and then we obtain different values for the prediction. And using this method, we can deduce the percentile confidence interval for the prediction. Also, when we make prediction, it's important to know if you make a lot of error or not. So we have used a Bryan score in order to evaluate the error of prediction. And in order to take into account the censoring, we took a weighted time-dependent Bryan score. So in this Bryan score, you have a difference between what is observed, like the vital status, minus what is predicted by the model. It means the probability to survive. And the sum is over the patient still alive and uncensored at time t. So in order to take into account the censoring, we use the inverse probability of censoring weighting, which is like this, and we were able to obtain an error of prediction. So using this kind of approach, we obtain an apparent error of prediction, and in order to know if the error of prediction is also good on new patients, we use also tenfold cross-validated approach. So in the application, we had more than 1,000 patients with a median follow-up time of 14 years. We observed more than 300 patients who died during the follow-up, and the mean number of recurrent events in the sample was only 0.4. So, as I said before, what we call the recurrent event here is a mixture of local regional relapses or distant metastases. So in order to fit the model, but also to propose some probability of prediction, we use the package, the R package Pretipacks, which have been developed in our team. So this is a part of the results that we obtained from the joint modeling. We obtained different prognostic factors associated both to recurrent events but also to death. Most of the time they had the same direction, but sometimes the effect could be different, except for age, which have not the same effect on recurrent events and on death. So at the end, we obtain a value of the variance of the random effect, which was significantly different from 0, which indicates that the recurrent event process and death were significantly associated with an alpha greater than 0. So it indicates that the effect of the unobserved covariance was much bigger on the risk of death than on the risk of recurrent events. So from a prediction point of view, we obtained this kind of table when we wanted to predict death between 5 and 10 years. We obtained this result, and we wanted also to check the evolution of the prediction results when we had a different number of, when the patient had a different number of recurrent events, but also when the time of the recurrent events were different. So when it was early recurrent event or late recurrent events. And in this table, we compare the 3 probabilities. The first 2 take into account the evolution of the history of the patient throughout recurrences. The last one do not take into account this into the prediction probability. So what we see is that the more recurrences you have, the higher is your probability of dying, from 10 to 67%, as it was a little bit expected. It shows also that P1 and P2 give similar results with the same tendencies, but P2 has some differences on when you have different recurrences, simply because it takes into account the last event in the calculus of this probability. So we observe different results. And also we can see that when the patient does not develop recurrences, we obtain quite similar results for the 3 probabilities. This is simply because 2/3 of the sample, didn't develop recurrent events. So this is probably why we obtain quite similar results. We also propose the prediction for the time between 5 and 15 years, and as expected, the probabilities were higher than the prediction between 5 and 10 years. And we can see also that the prediction when patients develop early recurrences give higher prediction than when people develop late recurrences. So here we are going to compare two patients with the same characteristics, except that patient 1 is going to develop recurrences, but not patient 2. And we wanted to compare the 3 probabilities here. So at the beginning, the probabilities of dying is the same over the 15 years of follow-up. But when the first patient develops the first recurrences, we see a major differences between P1 and P2 and P3. And when the patient develops a new recurrences, the difference increase between P1, P2 and P3. Same for the 3. So we have presented here also the error of prediction, but this is an apparent error of prediction after time 5 years. What we can see here is that the error of prediction was lower for the joint modeling, taking into account the evolution toward recurrences, and the error of prediction was higher for the two approaches who didn't take into account the evolution, like the Cox model or the P3. But when we use a cross-validation approach, we obtain quite similar results between the 4 prediction values. And as expected, the error of prediction was higher than the prediction on the apparent prediction, but it was not expected. The error of prediction was a little bit higher for the joint modeling P1 and P2. However, when we made this analysis on only patients who develop at least one recurrent event, we obtained what we wanted to obtain, means that the error of prediction was lower for when using all the information with P1 and P2. So to conclude, we have shown that it seems interesting to take into account recurrent events when you want to predict a terminal event like death, and joint modeling is a good approach in order to make prediction in this context. This is also a dynamic prediction simply because the time of prediction can move, and for the clinician you can improve your information. The patient is going to develop new recurrences, so it's going to be dynamic and it's going to evolve with time. And we have shown also that joint modeling gives better results than the classical Cox proportional hazard model in terms of error of prediction. However, we obtained that the tenfold causalization was a little bit unexpected. So this is probably linked to an overfitting, simply because we can have too much parameters in the estimation of the model. It could be possible also to use this kind of approach with conditional prediction. It means given the value of the random effect, but in this context with recurrent events, I think it's not interested and it's limited to say to a clinician that we can make prediction for a patient that we know. So it's interesting to make prediction for new patients. So conditional prediction, given random effect, are probably not interested in this context. So in the future, we are working on the external validation of this work with Audrey Morguen. She has a poster. And we have mainly worked on the prediction of death, but we would like also to work on the prediction of the progression themselves. And probably we could compare this kind of joint modeling using alternative models like additive prosperity models or something else with different